Hello class, we are on the next section, chapter 4.6. Today we're going to talk about modeling with exponential functions. So this is basically word problems. The next two sections are really all about word problems as it pertains to exponential functions. So some of these we'll solve by using the exponential function, and some of these we'll have to solve by taking the logarithm of the function in order to answer the questions that they ask. So it really just depends on the way that they form the question. If they're asking us for an input and they give us an output, we have to use the logarithm, right? If they're giving us an input value, what happens after this amount of time, for example, that's just, you just plug that into your function, and whatever you get out is the answer. So we'll go through a couple of models today, and we'll talk about how these functions can model different processes in real life. So let's first talk about doubling time. So we've talked about this a couple of times, but we haven't talked about it specifically as pertains to creating a function out of it, right? So we've asked questions like, how long until I have twice as many if I'm growing at this rate exponentially? And we found those answers by taking our output and then doubling it and then using a logarithm. So today we're going to actually have a model that we can use all the time for this. So let's say that it takes a time interval of n units for some sort of a population to double from its initial population, which is p naught. So this initial population can be given to us, or it can just be the only known population that we have, and we want to know how long it takes to double from that point, right? So my population is given at a time of t, so t is my input. My function is given as p of t equals p naught, my initial value. Here, this is my growth rate, right? I'm looking for things to double, and the exponential function is t over n, where n is that doubling time. Okay. So here, n and my time intervals are all measured in the same unit of time. So I'm not going to say it takes me 2 days to double my population, and then after how many years, right? So I wouldn't plug in 5 years and 2 days here. I'd have to change the years into days before I could do the math. So my t and my n, they have to represent the same unit of time. Okay, that's the only thing you have to watch out for, but that's generally not an issue when you're going through these problems. So let's go ahead and do an example. So let's say that we have a bacteria culture that has 1,000 bacteria present, and it's known that this bacteria grows at a rate of 2% hourly. What is the doubling time for the culture? So we have our initial value. We know we're looking for doubling time. However, the doubling time isn't given to us, this value of n. So we need to find this value of n here. So we have the growth rate, we have an initial value. So let's just set up our equation as normal. My function here, f of t, I can call it p of t, I can call it f of t, g of t, h of t, it doesn't matter. So here we'll just call it f. My initial value is 1,000. My growth rate is 2%, and it's growing hourly, so t represents the number of hours. Okay, we don't have to worry about compounding rate and things like that because my input is just every hour. So I want to know, when am I going to double in output, right? If I'm starting with 1,000, when am I going to end up with 2,000? So we set that as our output value, our function value. So we have 2,000 equals 1,000 times my growth rate raised to t. So here my goal is to now just isolate t. So I'm going to divide both sides by 1,000. And this should make sense to us also, because let's say that my initial value here, in this case, is 1 or 100%, right? I want to know when I double that, so I'm looking for when I come out with an output of 2. So whether I set this up as 1,000 and 2,000, or just my equation, right, just my growth rate, and an output of 2, right, where my initial value is 1, this still represents doubling, okay, because here initial value and double. Here the initial value is the invisible 1 we have times this 1.02 growth rate, and an output that's double that, right? So either way, it simplifies down to the same thing. So here I'm trying to isolate t, so I can take the log of both sides or natural log of both sides, and that will allow me to pull t down as a multiplier. Here I use natural log instead of regular log because it doesn't really matter, right? Log or natural log, both of those work. They're both easy to find on a calculator, as we've said before. I like using natural log, so I chose to do it in this example, okay? In order to finish isolating t, I will divide both sides by natural log of 1.02. So this is my exact value, but that's not going to help me a whole lot here because I'm not going to plug that in as my my doubling rate. So I'm going to go ahead and find my decimal approximation, and it's going to take about approximately 35 hours to double, right? 35.0027878 hours. A lot of this is unnecessary, right? I know a lot of times I say take it to 4 decimal places, but in terms of an hour, these are like microseconds. You know what I mean? So this 35 we can use as our approximation. It's approximately 35 hours for my bacteria to double, okay, in population. So we're going to use n is 35.00278878, but again, we're just going to use the value of 35 because it's very, very close, accurate enough for what we need to do, right? So we can approximate this doubling time with the function p of t is 1000 to, for doubling time, t over 35 because it takes approximately 35 hours, just a little bit over 35 hours in order for this population to double, okay, any population of this bacteria to double. So note that if we were to simplify this, 2 to the 1 over 35, which is coming from this part right here, right, that's very, very close to our growth rate that we use. Let's say we stay to the 4 decimal places of accuracy, 1, 2, 3, 4, right? Nothing would change. It would be 1.02 still. Okay, so our value of using 35 without 4 decimal places is pretty accurate. Ideally, yeah, we would use, 35.0028 here, but that's unnecessary for this case. Okay, so this is very, very close to original growth rate of just 2%, although it is off. Right? So if we wanted to model our growth rate with a continuous function, we can use what's called the relative growth rate. So again, for continuous growth rate, that's when you have a base of e, right? So if we have a base of e, that growth rate we call the relative growth rate. So this allows us to model the same function, the same instance, but with a base of e, continuous function. So what we do is we set this equal to each other. My initial value is 1000. For my continuous base of e, it's still initial value of 1000. Here my growth rate is 1.02. Here it's e raised to some power times t. I don't know this value of k, so I leave it unknown, right? I set these two things equal because I want the growth rate here to be the same as the growth rate here. My goal is to solve for k. So I'm going to start trying to solve for k. Here I can very easily divide both sides by 1000. And I get my growth rate equals my other growth rate, okay, with the input of t. Take the log of both sides, or the natural log of both sides. Natural log would be better because that'll help simplify here with this base of e. Okay. So we know the rules. When we have a base and an exponent inside of a logarithm, the t gets to pull out, and this kt gets to pull out as well. Now we have a multiple of t on both sides, so we can divide this entire equation by t. Okay. And we know that natural log of e is just 1. So my value of k is natural log of 1.02. Okay, because natural log of e, again, is just a value of 1. Right? Log base e with an input of e means e to the 1 is just e. Right? So natural log of e cancels out. And that's my k value. Now, it'd be nice to put natural log of 1.02 to t here as an exact value, but we typically don't do that. So we write our decimal approximation, which is almost 2%, right? 0.0198026273. So to 4 decimal places, that's 0198, right? If I went to 3 decimal places, yeah, that would round to 2%, but we need to be more accurate that because remember, continuous growth rate and a single growth rate are very, very, very close in value, but they're always off by a little bit. So my function p of t with an initial value of 1000 and a growth rate of 2% can be modeled equivalently with a doubling time of 35 hours with a growth rate of 2, right? Doubling time 2, same initial value. Or I can model it with a continuous growth rate function of initial value 1000 and then a growth rate of 0.0198 or 1.98%, right? Almost 2% as well. So all of these will give me fairly equivalent values. That's why here I put the approximate symbol because they'll be off just a little bit because especially since I used a value for the doubling time to be different. And then not only did I use the doubling time to be different, which will give me an error, when I made my continuous growth rate, I also had to cut off some values, right? So I set it equal to the 2%, not the function that I used where I had used approximations, this doubling time. I didn't set it equal to this to find the doubling rate. I set it equal to the original that had the exact value, but I did have to cut off some values here for the percentages, so this gets an approximate symbol also. Okay, so these should all be fairly approximately equal. Okay, so in general, if we have a periodic exponential growth rate of r, so here, this first one, this is periodic because it was hourly, right? This is still somewhat hourly. This is more for doubling time, but this is continuous, right? This is continuous. These two would be considered periodic. Then we can relate this to our continuous growth rate, the one that we did last for this k value, our relative growth, by the following equation. So I have 1 plus r raised to the t equals e to the kt. So just like I did here, right, at this point, and then solving for k. So solving for k, I'll always end up with k equals natural log of 1 plus r, which I did. K was natural log of 1 plus my growth rate of 2%. So that's how I relate my continuous relative growth to my periodic growth, right? This one was hourly, this is continuous. So that's how you can find out and rewrite it with the base of e. So now let's talk a little bit more about applications of exponential functions. So now we're going to get into finance. All right. So now we're going to talk about APR and APY. So you've probably seen these things many times when you see car commercials or whenever you want to try to borrow money or things like that. So now we can get into the nitty-gritty of these and talk about the differences and what they actually represent. Okay. So APR stands for annual percentage rate. APY stands for annual percentage yield, right? We also have what are called nominal rates and effective rates, right? So we're going to talk about all of these, the difference between APR and APY, and the difference between a nominal rate and an effective rate, and which one of these are which. So one of these is a nominal rate out of APR and APY, and one of them is an effective rate. So if you're given an interest rate, right, like in a commercial, but you have no information about the compound rate, right, which is, are they charging monthly? Are you getting charged yearly? Are you getting charged continuously? Are you getting charged daily, hourly? If none of that information is given, then that interest rate that you have been given, right, is called the nominal rate, right, or in name only. Because if you don't know the frequency of compounding, then you can't actually calculate any interest, right? So we saw this before, that, you know, we have our 1 plus r over n raised to the nt, where n is our compounding frequency. If we don't know how often we're being charged or we are being applied interest to our account that where we're saving money, then we don't know what our interest is. Right? This is typically how people get misled when they're watching a car commercial, or they're applying to in a bank account, or they're trying to invest money. You have to look at not only the interest rate, but the frequency of compounding, right? So APR rates are nominal, right? They're in name only. It's not how much percent interest you're actually gaining or paying on a loan or on an account, okay? The APY is an effective rate. It's how much you're actually paying, right? So APY is annual percentage yield. So it tells you how much you're actually paying or receiving within a year's time towards your interest, right? So it's the true rate that tells exactly how much interest is earned or paid in a year. So let's do an example. Okay. So a car commercial states that its new model for the year costs $40,000, okay, 40K. And it can be financed with zero money down with an APR of 3.25%. The nominal rate is 3.25% because they don't tell you how they're charging you on this account, right? Is that being applied continuously? Is it being applied daily? Is it being applied once a month? How is it being applied, right? Generally, however, we know, or we tend to know as we get older, that bills are compounded monthly, that you generally get charged every month when you have a bill. So our annual effective rate, or our APY, can be calculated with this, right? 1 plus my R, my nominal rate, over 12, because I'm being compounded 12 times a year. They're charging 12 times a year at this rate. And our rates to the 12 over 1 just because it's for 1 year, right? So this comes out to 1.032988512. Okay, so the amount that I have over 1, right, the actual interest, the actual rate is 3.299%, right, or 3.2989% if I cut it off there. So that's the actual amount of interest that I'm paying in a year, not 3.25%. So that's the difference between APR and APY. APY is how much you're actually paying in interest a year. APR is how much they're telling you you're paying in a year, right? So the relative growth rate for the year, so that's me equating this to a base of E. So I need to solve for K. So again, this is my how much I'm actually paying in a year, right? This 1.3989. So again, I'm using the exact value, because if I use this value to try to find the value of K, I am cutting it off and using a decimal value, and then finding a value, and which I will then cut off some more. So it's more accurate for me to use the exact value to find K, and then apply the decimal rounding up or down at 4 places. Okay. So when I find K, I take log of both sides, natural log of both sides, and I simplify it down, and we should get that natural log of this is the same as 12 times natural log of what's going on the inside equals K, because here natural log of e to the K, the natural log and e cancel, and we get just K. So if we calculate this, we get basically 3.246%, okay, which is different from 3.25 and 3.29. So all the values are different. My APR is different from my APY, which is different from my continuous growth rate. Okay, so that's my relative yearly growth rate, or my continuous growth rate. So to summarize, let's put this in the table. If my nominal rate, which is the same as APR, is 3.25%, then my effective rate, which is the same as my APY, is 3.2988512. So my APY is larger than my APR, right? Obviously, because it's being compounded monthly, not just once in a year, right? My relative growth rate, which is the value of K that I'm looking for when I'm talking about e to the KT, is 3.24560689. So it's actually pretty close to the actual nominal rate, right? It's very close. So if I want to calculate the effective rate, we generally have to subtract 1 from our calculation in order to isolate our percentage that's more than 100. So that was what we did here. When I had this 1.032988512, the amount larger than 1 is my growth, right? So I would take this value and subtract it from 1, and that's how I would get my growth rate. So if I want to find my growth, we have to remember that we have to subtract it from 1. So my effective rate is this 1 plus r over n to the n, right? However many times I need to compound in a year, minus my 1. So that's how I find my effective rate, because I need just the percentage, right? Just the percentage, not the 1 plus this, or the 1.032988512 value. Just the percentage over 1. So I gotta subtract 1. Okay. Here, r is my nominal rate, and n is the number of times that I'm going to compound that rate per year effectively. So again, for monthly bills, that would be 12 times in a month. 12 times in a year, I'm sorry. So the next thing we're going to talk about is radioactive decay. So radioactive substances decay by emitting energy through the process of particle radiation. So basically what it means is, basically like when you see an animal carcass when it starts to decay into dust, right? Radioactive substances do the same thing. Different substances take different times to decay, right? Some of these we know, some of these we still have to find out. So the time that it takes, n, for an amount of an element, which we'll call P naught, right? The initial amount of the element that we have, to decay to half of its amount, is known as the element's half-life. Okay, so again, some half-lives are very long, some half-lives are very, very short, right? So there's some elements who only exist for seconds, right? They decay in a matter of, in the blink of an eye. Some elements take thousands of years to decay, right, to half of their amount. So half-life is very, very important. It's how we are able to date things, how we run atomic clocks, things like that, right? Very, very important to understand half-life. So the amount of the element that is left after a time of t can be modeled with our equation. P of t equals P naught 2 to the negative t over n, right? Now, remember the way the exponents work? I can take just this negative and apply it as 2 to the negative 1, which will give me a base of 1/2, which makes sense because this is half-life. I want to know when half of an element is left. So same thing like doubling time. If the half-life is given, we just replace it with this value of n. Okay, so let's do an example. So the process of carbon dating is possible because there's, again, certain elements whose half-life are known. One of those is carbon-14, okay, which is known to have a half-life of 5,730 years. So carbon dating is only accurate if there is more than 0.25% of carbon-14 left in a sample. So some, like I said, things decay, right? So for instance, a fossil is not going to have enough carbon-14 left in it for us to be able to date it, because all the carbon-14 is basically gone, and the amount that's left is nearly undetectable. So it's not an accurate method of dating. Okay, so there's a limit. Okay, there's a limit to how far back we can date something, right? And we want to know that. What is the limit on the age of an object that we can date by using carbon dating? Because again, if there is less than this amount of carbon-14 in a substance, there's not enough for us to do this analysis, right? All of it is decayed already, basically. So I will set my equation equal to this amount, right? So 0.25% as a decimal is 0.0025. My half-life is 5730, so I replace that for n, and I basically just need to solve for t. The value of t will tell me how long would take for something that had 100% of its carbon-14 to get to a point to where the limit of my detectable amounts is, right? So I take log of both sides, or natural log of both sides. Like I said, I like natural log. So natural log of my decimal value on my left side, natural log of 1/2. The exponent pulls out to the outside as a multiplier. So from here, I just need to solve for t. So I'm going to divide both sides by natural log of 1/2 and multiply both sides by 5730. So my exact value looks like this. I would then plug this into my calculator to get my decimal approximation, because if I did it along the way, very likely that I get some decimal errors as I go, right? Some rounding errors. So the exact value is this. The decimal approximation is 49,529 and 29.597 years. So almost a third of a year more than this, right? So that's a very long time. So if we just round that to, like I said, it's a very long time. So if we round this up, it's basically 50,000 years old. Okay, so anything that's more than 50,000 years old, I'm probably not going to be able to date it, right? Anything that's younger than 50,000 years ago, I should be able to know how old that object is. Okay, so that's how carbon dating works. So the last thing we're going to talk about is Newton's law of cooling. So cooling happens when you take a hot object and you place it in a surrounding temperature that's cooler than that object itself. Like when you put something in the fridge, your fridge is cool, but whatever you put in the fridge was warmer than the temperature of the fridge, right? So that's cooling. Heating kind of works the same way. You're placing something that is cool into a surrounding temperature that's hotter. That would be a heating situation, right? But the formula actually works the same way. Okay, so here we're going to talk specifically about cooling. Okay, so Newton's law of cooling is that the initial difference between your object and its surrounding temperature, its ambient temperature, is d naught, right? So you would take your surrounding temperature and your object's temperature and you would subtract those values, and that would be d naught, which again can be calculated as Ts minus T naught. Ts is the temperature of your surroundings. T naught is the temperature of your object. Okay. So the temperature, which we'll call T, of our object after time t can be modeled with the following. The temperature of our object after t minutes, hours, seconds, what have you, is the ambient temperature, the temperature of your surroundings, plus the difference in temperature between your object and its surroundings times e to the negative kt. So we can expand this into all t terms as t of s plus t of s minus t naught times e to the negative kt. Okay, so again, time is plugged in here in the exponent position. K is our cooling constant, basically. Okay, the rate at which our stuff is going to cool. So let's do an example. Okay, a cup of tea is poured from boiling water at 212 degrees Fahrenheit. That's the boiling point of water. So you have a cup of tea, you have your tea bag in there, your tea leaves, and you pour your boiling water into your cup, right? So its initial temperature is 212 degrees. If the temperature in the room you're in is 70 degrees, pretty much the standard temperature of a room, especially in San Francisco, where we live in this case, and the temperature of your tea decreases to 180 degrees after 20 minutes, we want to know how long it's going to take until the tea is drinkable at 150 degrees Fahrenheit. Okay, so any more than 160, you generally are going to burn yourself. Under 130, it's going to start to feel a little cold. So generally, they say 130 to 160 is drinking temp. I know this because I worked at Starbucks for like 5 years, but that's besides the point. So let's say we get it down to 150 degrees. So my formula will look like this, right? Ts is the ambient temperature, the temperature of my surroundings, the temperature of the room. The difference between my object and the room temperature is 212 minus 70. I don't know what K is. right? So if I simplify this, right, I know after 20 minutes, so here my time is in minutes, I know after 20 minutes my temperature, my output, right, drops to 180. So this point of 20 and 180, if I plug this into my equation, I get out 180. 70 plus 142 equals negative 20K, right? The 20 I plugged in for T. So now, in my equation, the only thing I don't know is K. Remember, E is a value. I don't have to solve for it. It's a number, 2.714 something, right? K is what I don't know, so I'm going to solve for K. So I'll subtract 70. I will divide 142. And then I will solve for K by taking log of both sides, right? So I minus 70, it gives me 110, divide by 142. Now it's one thing equals one thing. I can log both sides, okay? And this is the value I will get for K, right? Log both sides. Negative 20K equals natural log 110 over 140. So in order to isolate K, I divide both sides by negative 20, right? So this is what I get for K. This is my exact value. I want my decimal approximation. So I plug this in and I get a cooling factor of about 0.127673346. So we'll take the first 4 decimals, round them up because the value after that is a 6. So 0.0128 is what we will use as our equation. Okay, so this is my equation. So in order to figure out how long it's going to take until this cools to 150, I have to now set this to 150 and solve for my T. Send this to 150, we get the following. Okay, so again, the only issue that we kind of have here is that we did cut off this, our values here. Right, so we're using rounded values, so our values are not exact, but it should be good enough for what we need to do, right? So remember, whenever you have to write the decimal and you have to cut off some information, round up, round down, whatever is going on, you're losing some info and you're going to get some sort of an error. Maybe it's large, maybe it's not, right? So we're going to use this function. We're going to set it equal to 150. Okay, so we're going to do the same thing. We got to solve for T. So I minus 70 on both sides and I get 80. Then I divide by 142. Now that my equation is one thing equals one thing, right? I can start to solve for T by either using the change of base formula. We're taking natural log of both sides, so we'll get natural log of 80 over 142, and this will turn into negative 0.0128 T. Okay. Isolate T by dividing both sides by this decimal value. This isn't very good as an answer because it doesn't tell me exactly how long it takes to cool to 150 degrees. So plug this in our calculator and it takes about 44 minutes, very close to 45 minutes, right? So 44 minutes and, 82% of a second, basically, or 82% of a minute, I'm sorry. So if I had to use exact values the entire time, I would have an exact answer. Right, so this is still an approximation, one because I have a decimal value, but also because I used an approximation value in here. So let's say that we use the exact value the whole time. My equation would be 70 plus 142e, not to this decimal value, but to that exact value, right? So it's very, very ugly, which is why we use our decimal approximations, right? If I went ahead and solved this, my T, instead of being 1 over negative 0.0128, it would be 1 over to my exponent, right? The 1 over 120, natural log 110, 142. Because that's how I got this point, that's how I got this value in the first place, right? Natural log 110 over 142 time divided by negative 20. Okay, so if I plugged in here, then when I solve for T, instead of 1 over the decimal value, it would be 1 over that power of my exponential base times natural log of 80 over 142. Okay, say I simplify this a little bit. The 20 jumps to the top because it's a decimal. So I got 110, 142. On top is natural log 80 over 142. This 20 it's a 1 over 20, so it goes on top. These two negatives cancel out to a positive. So if I plug this in to get my exact value, it's 44.94285153. So this would actually be, this is actually much more accurate than this, but look how close they are, right? So using 4 decimal points, it does give me an error, right? But it's fairly close. If I were to round this to the whole digit, I would get 45. If I rounded this to the whole digit, I would get 45, right? So they're very, very close, but notice that me being 4 decimal points in accuracy does not give me 4 decimal points of accuracy in my final answer. It only gives me, it actually gives me no decimal points, right? It's only accurate to the whole number. So it's not accurate to any decimal points, actually, even though I have 4 decimal points of accuracy here, okay? So just reiterating this idea of error, because this comes up more so now, you know, when you're calculating exponentials and logs and natural logs, this is where the errors start to accrue. We'll see it when we do the trig stuff as well. So it's just important to point this out continually, that whenever we have a decimal and we have to, you know, round down or round up at some decimal point, we're having some error, right? So obviously the more decimal points I have, the more accurate. So, you know, the least amount that I keep, the more error I'm going to accumulate as I do, right? But if this is my final step, we, you know, we try our best to cut off our values at the final step so we don't have any error.